Hi, everyone. Before I begin, I would like to thank the organizers of Cosmology from Home for giving me the chance to speak at this very cool conference. My name is Laura Herold. I'm a postdoctoral fellow at the Johns Hopkins University. And the title of my talk is Cosmological Tensions and Statistics. And in particular, I would like to talk about insights from both Bayesian and frequentist approaches. But first, let's take a step back and consider the status of cosmology. So the lambda CDM model, which is the standard model of cosmology, has only 6 parameters and fits most cosmological data extraordinarily well, apart from some famous tensions and anomalies. However, about 95% of the energy content of the universe is dark. So for many years, we are left with the questions about what is dark matter? What is dark energy? Are there more components or more interactions? So how can we make progress? One approach to make progress is to stress test the lambda CDM model with all possible observations and look for places where the model breaks down and inconsistencies and tensions appear. And maybe possible such hints have already been found, which could be the H0 and sigma 8 parameter discrepancies. And first, I would like to talk about the H0 tension. So the H0 tension is a discrepancy in different measurements of the current expansion rate of the universe, H0. And in particular, this tension is most severe between the measurement by the cosmic microwave background and the distance ladder measurements. For example, the distance ladder based on Cepheid calibrated type 1a supernovae from the SHOES collaboration. And the tension is at a level of about 5 sigma now, and is still unresolved. But the interesting part about the Hubble tension is that it's not only a tension between 2 experiments, but between 2 classes of experiments. On the one hand side, there's the indirect measurements, for example, the CMB measurements, the baryon acoustic oscillation measurements, and galaxy clustering measurements. These measurements are typically precise, but they depend on the cosmological model that is assumed. So these measurements constrain the universe, or the CMB, for example, constrains the universe at early times and needs to assume a cosmological model, usually lambda CDM, in order to predict the expansion rate today. On the other hand side, there are the direct measurements, which are, for example, the distance ladder measurements or gravitational lensing measurements, which often have a larger uncertainty due to astrophysical modeling, but they're independent or almost independent of the cosmological model. Now, apart from the H0 tension, there's also another discrepancy that has appeared, which is the so-called sigma 8 discrepancy, where sigma 8 is basically a measure of the homogeneity of the universe. And sigma 8 can be computed as an integral of the linear power spectrum over wave number k, smoothed with a top-hat filter with radius of 8 megaparsec over h. And then the S8 parameter is simply given by sigma 8 times the square root of omega matter divided by 0.3. And it turns out that the Planck CMB prefers 2 to 3 sigma higher S8 values than weak lensing, share, and clustering experiment, like the Dark Energy Survey, KIDS, and HSC. So how to solve these tensions? The most common approach is to start from the lambda CDM, the 6-parameter lambda CDM model, and to add extra components or interactions. And this leads to nested models of the type lambda CDM plus X. And these models can have several additional parameters and can be arbitrarily complicated. However, adding more parameters can lead to degrading of constraining power. And this in turn can lead to strong dependence on the analysis choices and priors. So in this talk, I would like to illustrate these points in the context of the 2 tensions. So in the context of the H0 tension, I would like to illustrate this with the example of early dark energy. And in the context of the sigma 8 tension, I would like to go into more details about the constraints from Boss and the effective field theory of large-scale structure. And in particular, I would like to discuss frequentist parameter constraints because these have become more and more popular in the recent literature. So this is the outline of my talk. I would like to begin with a case study of the early dark energy model and the Hubble tension. Then in the second part, I would like to give an overview about Bayesian and frequentist parameter constraints, and in particular discuss the different interpretations of these two statistical approaches. And in the third part, I would like to discuss the question, when is it important to diversify statistical approaches? So let's start with early dark energy and the Hubble tension. In order to understand how to solve the Hubble tension with new physics, it is instructive to look at this quantity theta s, which is the angular size of the sound horizon. And it is given as the ratio of the physical size of the sound horizon rs divided by the angular diameter distance dA, where rs is given as an integral from the redshift of recombination, c star, to the Big Bang, where dA is given as an integral from today to the redshift of recombination. Now, theta s is very precisely measured by the CMB. It's given by the frequency of the acoustic peaks in the CMB power spectrum, and therefore one can assume basically theta is fixed by observation. And this leaves us with two options to solve the Hubble tension. One of the options are the so-called early time solutions, which modify the physics between the redshift of recombination and the Big Bang. So they modify rs, whereas the so-called late time solutions, they modify the physics in the later universe, so between today and the redshift of recombination. And it turns out that early time solutions seem to work better. Roughly speaking, simply because there's more wiggle room at early times than at late times, where at late times, we have lots of constraints of the expansion history between today and the redshift of recombination coming from supernovae and baryon acoustic oscillations. So early dark energy is an early type solution. And the idea behind early dark energy is the following. So early dark energy introduces an additional component in the early universe, which boosts the expansion rate h of z. And therefore it suppresses this whole integral here and reduces the physical size of the sound horizon rs. Now, because theta s is fixed by observation, if rs decreases, also dA has to decrease. Now, if we look at h of z, and we assume the meta content is similar as in lambda CDM, the easiest way to accommodate this additional ED component in the early universe is by increasing h0. And this is what is needed to solve the Hubble tension. The most commonly studied model of early dark energy is the so-called axion-like early dark energy model, which consists of a scalar field with a 1 minus cosine potential. And this model is a very phenomenological model. It has three parameters that need to be fit from the data. One is the mass, which appears here in V0 in the normalization of the potential, then the so-called decay constant F, and the initial value of the scalar field in this potential here. Then in principle, there would be a fourth free parameter, the index of this potential, but it is customary to fix this index to 3, because it has been shown that this is the number that fits the data best, and it ensures that EDE decays quickly enough. So the EDE field is a field with an extremely small mass of around 10 to the minus 27 electron volt. So let's have a look at the dynamics of the EDE field, which are governed by the Klein-Gordon equation. Initially, the field is dominated by Hubble friction, so it is frozen in its initial position and behaves like dark energy. At some critical redshift, the potential term becomes larger than the Hubble friction term, and the field starts to roll down the potential and to oscillate around the minimum. And one can show that in this phase, the field decays faster than matter. So to summarize, the equation of state for this early dark energy model is W equals -1 for redshifts earlier than the critical redshift, and a time averaged W of n minus 1 over n plus 1, which equals 1/2 for n equals 3 for redshifts later than this critical redshift. And this is what the fraction of early dark energy as a function of redshift looks like. At early times, so here on the right-hand side, one has this rapid increase of the energy density in early dark energy. Once the field starts oscillating, it starts to decay. And at recombination at around redshift of 10 to the 3, the field is almost already completely decayed. So from the particle physics parameters, mass, decay constant, and initial value, one can calculate the more phenomenological parameters, which are FEDE, the maximum fraction of early dark energy at the critical redshift CC, which is when the field starts oscillating, and the initial value of the scalar field in the potential. So this model has 3 additional parameters compared to lambda CDM. And in order to solve the tension, one typically aims at about 10% of FED. So can ED solve the Hubble tension? Here I will only focus on a few references in order to keep the discussion more concise. If one considers the following data sets or similar data sets, like the Planck CMB data, 6D FGS, and BOSS baryon acoustic oscillation or full-shape data, plus the Pantheon supernova and the SHOES supernova samples. Then one typically finds that these data sets prefer rather high fractions of early dark energy of around 10%, which increase H0 to about 70.5 here in this example, which is enough to resolve the Hubble tension and bring back concordance with the SHOES direct measurement, which can be seen here in the plot on the right. So the orange is the lambda CDM model. EDE manages to shift H0 to higher values and increase the error bar, which reduces the tension with SHOES to below 2 sigma typically. So one could say that there's a strong preference for early dark energy if one uses these data sets. So one could conclude that early dark energy can solve the Hubble tension. However, if one excludes the SHOES direct measurement and other direct measurements from the analysis, one finds a different picture. So for example, here, if one also includes weak lensing experiments, one finds a very tight upper limit on the fraction of early dark energy, and an H0 that is consistent with Planck and inconsistent with the SHOES direct measurement, so not resolving the tension. So here in blue, you can see basically all data sets. If one now includes SHOES from all data sets, one finds this teal line, which gives this very tight upper limit on the fraction of early dark energy. So if there's no SHOES in a data set, one doesn't find a preference for early dark energy. And from this very tight upper limit, one could conclude that early dark energy is ruled out. However, several authors in the literature pointed out that volume effects could affect the results of the early dark energy model. So what are volume effects, also known as prior volume effects or projection effects? For that, I wanted to show this simple example here. Consider an experiment that measures 2 parameters, alpha and beta, and has this very non-Gaussian posterior contour. And here on the right-hand side is the same posterior contour in 3D. But now let's assume we're more interested in the parameter alpha. So we might want to compute the 1D marginalized posterior in alpha, which is obtained by integrating over beta. Now, this non-Gaussian extension just appears as a extended tail here on the right-hand side. Now assume we have a second experiment, experiment 2, which is only sensitive to alpha and gives this blue contour here. If we plot this in the 1D posterior, it simply appears as this blue Gaussian here. Now, if we were to combine experiment 1 and experiment 2, we would tightly constrain alpha and beta. And in the 1D posterior, this contour coincides with experiment 2. So what might be confusing at first sight here is that although for experiment 1, alpha equals 0 and alpha equals 5 fit the data equally well, alpha equals 5 is outside of the 2 sigma confidence interval for experiment 1. And one sees an apparent tension between experiment 1 and experiment 2 of about 3 sigma, which would not be present if one looked at the 2D posterior. So sometimes it can be misleading to look at the 1D marginalized posterior if the shape of the posterior is very non-Gaussian. Here, the example is obvious because one can look at the 2D posterior, but in real-life applications, the parameter space is often multidimensional, and then it's not as easy to see this. So in more generality, prior volume effects, they can appear if the posterior is influenced by the prior volume. And reasons for this are that the model has too many parameters, or equivalently, that the data is not constraining enough for all of those parameters. Or if the parameter structure of the model generates large volume differences. And this happens often with nested models. For example, in the case of the early dark energy, we have the fraction of early dark energy, which basically controls the amount of early dark energy, and two parameters, theta I and cc, which describe this early dark energy more closely. However, if FED equals 0, we recover the lambda CDM model, and in the lambda CDM model, theta I and cc are completely unconstrained. That means now if FED goes to 0, theta I and cc are completely unconstrained. Therefore, there's much more volume in FED of 0 than in FED larger 0. And when one marginalizes over theta I and cc, this can lead to preference for FED of 0 in the marginalized posterior. So one idea to explore this problem more closely is to use the profile likelihood, because the profile likelihood does not depend on priors. So the profile likelihood is a method from frequentist statistics that is used to construct parameter constraints. And the profile likelihood is based on the chi-square, so the goodness of fit to the data, which is given for a Gaussian as -2 the log likelihood. To compute the profile likelihood, one fixes the parameter of interest, which is called y here, to different values in the range of interest, and one minimizes the chi-square with respect to all other parameters of the model. So basically all nuisance parameters and all other cosmological parameters. And this gives the delta chi-square as a function of the fixed parameter y. And therefore, one minimizes out the nuisance parameter, which is also called one profiles over the other parameters instead of the Bayesian marginalization. Now one has obtained the profile likelihood, and from the profile likelihood, one can simply read off the confidence interval with a graphical method. For example, to read off the 1 sigma confidence interval, one looks for the intersection of the delta chi-square equals 1 with the profile likelihood, which would be here, and this gives the 1 sigma confidence interval. And for 2 sigma, one looks for the intersection of the profile likelihood with delta chi-square gives 4, and so on. So now coming back to the early dark energy model, if one computes the MCMC posterior of the Planck and Bose dataset, one finds this very tight upper limit on the fraction of early dark energy and this low H0 consistent with Planck. Now, if one uses exactly the same dataset but does a profile likelihood analysis, one finds that the data prefers high values of FED of about 9%. And one finds that it prefers high values of H0 of about 70.5, which is consistent with shoes at 1.4 sigma. So here in green is the profile likelihood in H0. In the gray shaded area, you can see the shoes direct measurement, and in the orange shaded region, the Planck H0 measurement. So in this plot summarizes constraints from the profile likelihood for 4 different datasets. And for comparison, the constraint for Planck and Bose data from the MCMC posterior. And one finds that the MCMC posterior prefers values of H0 which are inconsistent with shoes, whereas the profile likelihood prefers values of H0 which are consistent with shoes at less than 1.7 sigma for all the datasets that were considered in this study. So in this example of the early dark energy model, the Bayesian and frequentist approaches give very different results. So that brings me to the next section. And in this section, I want to discuss in more detail Bayesian and frequentist parameter constraints, and in particular, what are the different interpretations and how to do a frequentist analysis. To set the stage, I would like to start with Bayesian credible intervals, because they are more common in cosmology. These are based on the Bayes theorem, which states that the posterior, which is the probability of the model parameters given the data, is proportional to the likelihood times the prior. Now, the prior encodes prior information and beliefs. And a common question is how to choose the prior. Because if the data is not very constraining, that means if the likelihood is very flat, then the posterior is dominated by the prior. So in these cases, an analysis of the sensitivity of the results on the choice of prior is important. So if one has the posterior, one can simply obtain the credible interval by integrating over the posterior and requiring that this is equal to the confidence limit, confidence level alpha. And the method to obtain the posterior is typically from Markov chain Monte Carlo analysis, so from MCMC analysis. To obtain the 1D marginalized interval, one can simply integrate out all the nuisance parameters. So the interpretation of the Bayesian interval can be summarized with the following statement. Given the data and the priors, I believe that the true value of the parameter is within the confidence interval with probability alpha. So the Bayesian interval is based on the degree of belief. Now, the frequentist confidence interval is based only on the goodness of fit to the data, so only on the likelihood. So there's no prior, which means there's no straightforward inclusion of prior beliefs and no weighting by volume. So the constraint is only based on the goodness of fit to the data. And then the interpretation can be phrased as follows. The true value of the model parameter is contained in the interval, a fraction alpha of the experiment. So the frequentist confidence interval gives a statement about the repetition of the experiment. And this interpretation is also denoted as the coverage. So if the statement holds true, one says that the confidence interval covers the true value of the parameter. The method to construct frequentist confidence intervals is the so-called Neyman construction. And in the limit of a large data set, this construction simplifies to the profile likelihood construction. So the Neyman construction works as follows. Before even looking at the data, one constructs the Neyman belt, which I describe here for one parameter, so one dimension. The first step is to obtain the probability density function, which is the probability of the measured parameter given the true model parameter. But the measured parameter could, for example, be the maximum likelihood estimate, so the parameter that maximizes the likelihood. To obtain this PDF, one typically needs to simulate 10,000s of mock realizations of the data for different choices of the true value of the parameter. And for a given true value of the parameter, one constructs the confidence interval such that the integral over the PDF, which was obtained from the mock realizations above, equals the confidence level alpha. And this is shown, and repeating this for different true values gives the Neyman belt. And this is shown here on the plot on the right-hand side. For every choice of the true value, one generates mock realizations in order to obtain the PDF. Then from the PDF, one obtains the confidence interval, which are seen as here the red stripes. And repeating this for different true values gives a belt in theta true, theta measured space. So once one has obtained the Neyman belt, one can have a look at the actually measured value of the parameter. And one obtains the confidence interval at the intersection of the value of the measured parameter with the Neyman belt. So, for example, the 68% confidence interval is given by these red dashed lines. And the 95% confidence limit is this blue dashed line. So this would be an upper limit in this case. Unfortunately, the Neyman construction is numerically very expensive because it requires many mock realizations in order to obtain the PDF for the different values of theta true. And this is where the Wilks theorem helps, where the Wilks theorem describes cases where the complicated Neyman construction can be simplified by a proper likelihood construction. And the theorem states that in the asymptotic limit of a large data set, the likelihood ratio test statistic, which is defined as -2 times the log likelihood, where this is the likelihood of the data given the model parameter divided by the likelihood of the data given the measured value of the parameter. And this quantity follows a chi-square distribution in the limit of a large data set. And in this limit, one can safely use the graphical profile likelihood method, which in this case ensures the correct coverage. And to illustrate this Wilks theorem, I prepared a toy example. So consider to draw realizations from a Gaussian with mean mu and variance sigma, where for simplicity, sigma and mu are set to 1. So here's the histogram of these mock realizations. Now for each of these mock realizations, one can compute the likelihood ratio test statistic, which is then given by the likelihood of the measured value given the true value, which we know in this case, divided by the likelihood of the measured value given the maximum likelihood estimate, which in this case equal each other. And since we're computing the -2 log likelihood, this gives a parabola as a function of mu hat. And now if one plots a histogram in the likelihood ratio test statistic, one finds that this follows a chi-square distribution here. And from this, it is easy to see why the profile likelihood construction works in the case of a Gaussian, because then by construction, 68% of the mocks lie within the likelihood ratio test statistic smaller and smaller equal than 1, so lie in this purple range. And from this, one can construct a confidence interval in mu, because now it is guaranteed that 68% of the mocks lie within this confidence interval here. So at the intersection of the profile likelihood with delta chi-square or TLR equals 1. However, if one computes the profile likelihood from real data, the correct coverage is not ensured if the profile likelihood looks parabolic, because for correct coverage, this statement must hold for every value of the true parameter, not only for the one that is realized in nature. So how to compute a profile likelihood? The main ingredient is an efficient minimizer interfaced with a Boltzmann code. And I'm aware of 3 codes that can efficiently compute profile likelihoods: the camel code, which is based on gradient-based minimizer, and the more recent prospect and propoly codes, which are based on simulated annealing minimizers. And then soon there will be our code, the pink code, which is also based on simulated annealing. So simulated annealing works as follows. One runs several small chains, for example, with MCMC sampler like MontyPython. And these chains have successively decreasing step size and successively decreasing temperature, which means enhanced sensitivity to the likelihood difference in the Metropolis-Hastings algorithm. So the acceptance probability P is not only given by the likelihood difference, but it can be tuned by the temperature T. And what this means intuitively is that the chains in the beginning have large step size and large temperature, so they can escape local minima and explore the whole likelihood surface. And once the chains cool, so the temperature goes down, they get trapped in minima. And this allows to explore the region around the global minima in more detail. So to summarize this section, I have a table to compare Bayesian and frequentist intervals. So Bayesian intervals, they include prior knowledge as prior. So the posterior is proportional to the likelihood times the prior. So by construction, they identify bulk volumes that fit the data well. The problem, as we already discussed, is if the data is not constraining enough, there can be prior dependence and effects. On the other hand side, the frequentist intervals, they're only based on the likelihood or the chi-square. So there's no prior and no volume weighting. And this can lead to the exact opposite problem, because since profile likelihood is only sensitive to the goodness of fit, it can prefer a cosmology with very small parameter volume, so very finely tuned parameters. But the good news is that in the limit of a large data set, both statistical approaches should agree. And this brings me to the third section. When is it important to diversify statistical approaches? And for that, I want to discuss 3 examples from the literature. And I want to start with results from the Planck collaborations in 2013, where they compared the MCMC results to a profile likelihood analysis. So they used the profile likelihood analysis to verify the constraints on all lambda CDM parameters. And they find almost exactly matching constraints for all parameters in MCMC and profile likelihood. So this illustrates that in the limit of a large data set or few parameters, both statistical approaches agree. For the next example, I would like to switch gears a bit. So from CMB to large-scale structure. The conventional way to analyze large-scale structure is to identify the baryon acoustic oscillation scale, which is an imprint of the size of the sound horizon in the galaxy distribution. And use only this BAO scale to extract cosmological information. Now, the goal of the effective field theory of logic structure is to not only use this BAO scale, but use the full shape of the galaxy power spectrum. So not only the wiggles contained in the galaxy power spectrum, but the full shape. And this can be done by a perturbative approach to model the galaxy power spectrum. So the galaxy power spectrum multipoles have the following form. They consist of a tree part, which is 2nd order in the density contrast, a 1 loop part, which is 4th order in the density contrast, and noise contribution, which includes stochastic noise, and the so-called counter terms, which absorb the back reaction of the smaller scales onto the larger scales that are used in the analysis. And there are different codes to predict the EFT of LSS. So there's class PT, Pi-Bird, Velociraptor, and class 1 loop. And all of these codes and parameterizations introduce many new nuisance parameters. Here, the case of class PT are 8 additional nuisance parameters for each BOSS dataset. So these include galaxy bias parameters, counter terms, and shot noise. And typically, in all of these codes, flat and Gaussian priors are put on these nuisance parameters. However, if one uses the EFT of LSS to constrain sigma 8 with a BOSS full-shape galaxy clustering, one finds a curiosity, namely that the class PT and Pi-Bird parameterizations give different values of sigma 8 for the BOSS full-shape galaxy clustering. So where class PT finds a sigma 8 of about 0.69, Pi-Bird finds a sigma 8 of about 0.74. So it's closer to the Planck result of sigma 8 of 0.81. So if one uses Pi-Bird, one might conclude that there's no tension at all between Planck and the BOSS galaxy clustering. However, with class PT, one might conclude that there's a small tension between Planck and BOSS. So although class PT and Pi-Bird are actually mathematically equivalent parameterizations of the same theory, they give different results. And the question is whether these different results are due to the different priors that are used in the 2 different codes. And in order to explore this, we use the profile likelihood, again, since it's inherently prior independent. And we find that the profiles from Pi-Bird and class PT parameterizations actually give coinciding constraints on sigma 8 for the profile likelihoods, which can be seen here on the right-hand side as the orange solid line and the blue dotted line. So the profiles give the same results where the MCMC posterior can be seen here in the dashed lines, and they slightly differ. They are consistent with each other, but since this is relevant in the sigma 8 tension, is still interesting to understand where this shift comes from. So we also find that the profiles prefer higher values of sigma 8, which are consistent with Planck. But we also find that the uncertainty of the profiles is a factor of 2 larger than the MCMC posteriors. And in order to understand where this huge loss of constraining power comes from, we promoted the priors to actual data sets such that we can also use them in profile likelihood analysis. And this is shown here, where the black line here shows the prior in the West Coast, so in the pi-bit parameterization, and the red line shows the profile in the class PT parameterizations. And one sees that the error bar shrinks again to the normal size of the MCMC, which shows that actually the prior helps to gain the constraining power, that we see the difference in the profile and MCMC. So overall, we find a strong impact of the prior in the Bayesian constraints. Moreover, we did a simple forecast of what the MCMC and profile likelihood results would look like for a DESI-like volume. And we find that the results of profile and MCMC move closer together. So more data will hopefully help to reconcile both statistical approaches. However, one may be food for thought, because next generation experiments will also have higher accuracy. So it might be necessary to have more nuisance parameter. And if this is the case, it might be that this problem actually persists, and one needs to think about this more. Another idea to investigate this problem is to use a different prior. The authors of this paper use the so-called Jeffreys prior, which is a prior that is constructed such that it is invariant under reparameterization of the theory model. And they find a strong dependence on the prior, whether they use Jeffreys prior or Gaussian priors. And they find that the posteriors on the nuisance parameters often are dominated by the prior, which can be seen here on the right-hand side, which shows the standard deviation of the prior compared to the posterior. So if this fraction is 1, the posterior and the prior have the same error bar, basically. So the posterior is dominated by the prior. And they found also that Jeffreys prior can reduce biases on the results of the nuisance parameters seen in simulations. And they find that the parameters from a full-shape Boss analysis are consistent with the CMB. So both in this analysis and the profile likelihood analysis, there's no discrepancy in sigma 8 between Boss and Planck. And for the last example, I want to go back to the early dark energy model and want to mention this paper where the authors looked at an alternative Planck pipeline, the so-called NPipe and ChemSpec pipeline, which uses different analysis choices and more data than the conventional Plick pipeline. And this pipeline gives a smaller lambda CDM residual and tighter constraints on early dark energy. So with this new Planck pipeline, the evidence for early dark energy goes down, and the data prefers lower values of H0, which are inconsistent with shoes in the EDE model. And they use both Bayesian and frequentist approaches, which agree in this case. So maybe we have reached the limit of a large data set where both approaches agree, but there's still caveats because it is still unclear why this pipeline gives very different results from the Plick pipeline in this case. So with these 3 examples, I hope that I illustrated that when the data is not constraining enough, or equivalently, the model has too many parameters or nuisance parameters, which can be also important for next generation experiments, that in this case, there can be a strong prior dependence in the Bayesian analysis. And therefore, of course, it's important to not only conduct one black box analysis. Here, I showed mainly frequentist analysis as a possibility to check for prior dependence. But of course, there are many more possibilities, like a sensitivity analysis of the choice of prior, simple chi-square tests, or simply using a different MCMC sampler than the basic Metropolis Hastings sampler. And in general, it is important to adapt the statistical method to the problem at hand in a case-by-case basis. But of course, different prior assumptions and statistical methods are a personal preference. So only more data will help to resolve differences in these different approaches. And this brings me to my summary slide. Frequentist and Bayesian methods are complementary because they have different advantages and different problems. We discussed fine-tuning and prior effects. If there are too many parameters or nuisance parameters, a more in-depth analysis might be necessary. For example, prior sensitivity analysis or frequentist analysis, especially for nested models of the type lambda CDM plus X. And I presented insights on early dark energy and the effective field theory of large-scale structure. And of course, there's many more which I didn't have time to talk about. So thank you for watching, and I'm looking forward to the discussion sessions.